Okay, we're now recording, and I'll upload this recording to our Unit 2 playlist. So many approach schools require applicants to take a standardized test. Suppose that 1,000 students take such a test. Several weeks after the test, P receives his score report. He got 63, which places him at the 73rd percentile. What does that mean? So what that means is that he scored better than 73% of the people who took the test. And what I'm going to do is I'm actually going to have each person in this room. If you guys don't mind turning on your videos, that'd be great, so I can see you guys. So if everyone can turn on their videos, that'd be awesome. I'll wait.
Mr. Lashny?
Yeah, go ahead.
Because I'm using another computer to like attend class today, and this computer does not have a camera, and the usual computer
That's fine.
that I use,
okay.
Like, yeah.
Thank you for the explanation. I appreciate that. Okay.
Thank you.
And so I'm just going to go based upon just who I see first in the video. So again, I'm going to kind of like give you a little hint, and then you kind of help me figure out the answer for each of these questions. And there's 9 of you guys. There's 10 questions we'll do. So again, for number 2.1, the question is, 1,000 students take a test. Several weeks after test, P received a score report. He got 63 on the test. That placement was 73rd percentile. That means he scored better than 73% of the people who took it. So that means he's the top 27%. So he's at top 27%. Everyone else is lower than him. 73% is everyone else. So Zach, what do you think the correct answer would be based upon my reasoning there? You're the first person I see. And you're muted, by the way.
Sorry. I think it would be that he is better than, or he did better than 73%.
So what choice would you go with? If you look at my.
Oh, sorry. D or E. Sorry.
E. Yep. Very good. Thank you, Zach. So the answer would be E for this one, because definitely, who cares? He got a 63, so you don't say 63%. The 73rd percentile means he did perform better than 70% of the people who took the test. So he's a top 27%. So thank you very much for that, Zach. Okay, John, you can help me with the next one, but I'll kind of get us started here. So for normal distribution shown, the standard deviation is closest to. So if we take a look at it, this is a little tricky. So this is going to be in the middle. It's actually x equals 2. I would probably suspect that this would be 3 standard deviations, like a negative z-score of 3 and a positive z-score of 3z here. And again, it's a little tricky, but I'd probably put this right here, negative 2z and positive 2z. Remember, z equals this. So when you're 1z, that means you're 1 standard deviation away from the mean. When you're 2z, you're 2 standard deviations and so forth. Or if z equals 2, I guess that's a better way of putting it. So probably not the best question here. It's a little flawed, but it seems as if 34% of my data, I think you probably would need to know that. 34% of my data is right here, 34% of my data is right here. That would be with the 1 standard deviation. And actually, I should call it 1 sigma, not z. So let me erase these here. Let me change colors too. So 1 sigma, 2 sigma, 3 sigma, 1 sigma, or negative 1 sigma, negative 2 sigma, and negative 3 sigma. And I probably would say about maybe, because it's supposed to be middle 95%, half that's 47.5. So I'd probably say about 13.5% be over here, and 13.5% over here, and probably about 2%. So if you were to do the math and add it all up, your middle 99% would be between 3 standard deviations. So John, this is gonna be a little tricky. There's probably 2 answers you probably could go with. What would you say would be your answer for 2.2 here?
2 or A or C.
Well, the thing is, it's two tick marks. But we're going from 2 to 6 though. So how wide would you say this is? Just look at the graph. So this part that I'm highlighting right now, how wide would you say that is, John? But go ahead, John, you can speak in your microphone, you're muted.
4.
4. So it's a little tricky. So what choices do you think could work or close enough?
3 or 5.
Yeah, and so it's a little of a weird question. I'm not sure what we could exactly say, but I think you would need a little bit more details. And so this question is a bit vague. But it's a good review of the 68, 95, and 99. Remember, these two here at the 68. If I include these right here, I have 34 plus 34 plus 13.5 plus 13.5. So that's 68 plus 27, which is going to be 95. And then, of course, if I add these here, then I get 99%. So when you're within 1 standard deviation, whether you're above or below, that's the middle 68%. When you're within 2 standard deviations, whether you're above or below, that's going to be the middle 95%. When you're 3 standard deviations, whether you're above or below, that's going to be the middle 99%. So thank you, John, for helping me out there. Okay, let's move on to 3. Yes, go ahead, Teddy.
Why is like the 34% taking up 2 tick marks in this problem again?
I just don't know. I just made that up because I think we need more details.
Okay.
So I just think this graph was just a little bit off.
Okay.
I think you need more details to be able to answer that question. I just made that up. But that's where you're going to have one standard deviation, right? When you have that 34% region, whether it's above or below. But together, when you're both -1 and 1 standard deviation, that's going to be 68%.
Yeah.
So Teddy, you're actually going to help with the next one. Let me read it out loud. Rainwater was collected in water containers at 30 different sites near an industrial complex. The amount of acidity pH level was measured. The mean standard deviation of the values is 4.6 and 1.1. Okay. When the pH meter was recalibrated back to the laboratory, it was found to be in error. Okay. The error can be corrected by adding 0.1 pH units to all the values, then multiplying by 1.2. Okay. So you can correct there by adding 0.1 and then multiply by 1.2. So what are the mean standard deviation of the corrected pH measurements? Now, before we get too carried away here, let's say, for example, just being hypothetical. So before you answer, Teddy, let's say I have like just 5 numbers. Obviously, my mean is going to be 3, right? So if I add 0.1 to each of these, what do you think my mean would be now, Teddy? If I added 0.1 to each of these numbers?
They'll still be the same.
No, the mean. The mean was 3 originally, but by adding 0.1 to each of them, 3.1 exactly. But what about the standard deviation? Would that change?
No.
No, good. But definitely the mean would change. Now, what if I, after adding 0.1, then I decide to multiply by 1.2? Will that also change the mean?
Yes.
So, of course. So if I add 0.1 to this, and then multiply by 1.2, so now it's 4.7 times 1.2. So what would be the new mean, Teddy, for that one? You have a calculator, or you can use a cell phone if you have a cell phone nearby.
Yeah, 5.64.
Good. So now I know the answer is going to be either A, B, or E. So I can cross off C and D, just using the process of elimination. Now this is where it gets a little interesting. We know that adding 0.1 doesn't really change the standard deviation, right? So that kind of makes kind of makes sense. But we do see different standard deviations here. It's not 1.1 anymore. So adding 0.1, I don't think quite does it for us. So I'm going to cross off E. Because if I have 1, 2, 3, 4, 5, or 1.1, 2.1, basically the bottom line is that standard deviation is calculated like this: x minus mu squared, or x1 minus mu squared, plus x2 minus mu squared. That's the formula we'd have. And then we square root that whole thing, then we divide by n. But if your mean changes and each data point changes by the same amount, like if I add a 0.1, the mean changes by 0.1 and the data point changes by 0.1, that doesn't change this quantity here. However, if I multiply by something, so if I just multiply by 1.2, this becomes, all these change obviously. I get 1.2, 2.4, 3.6, 4.8, and 6. And that becomes 3.6. Now when I take the difference, these differences change. Before, if I subtracted 2 from 3, I had -1. Now if I do 2.4 minus 3.6, that changes. So Teddy, would multiplying change the standard deviation?
Yes.
It would. What do you think the new standard deviation is going to be now? If I have to multiply this by 1. So adding 0.1, forget it. That didn't do anything. So it still stayed at 1.1 by adding 0.1 to this, by adding 0.1 to all the data points. But if I multiply 1.1 by 1.2, what do I get now? You use a calculator yourself.
1.32.
1.22. Perfect. Thank you very much, Teddy. So adding does not change the standard deviation when you add numbers to each data point, but multiplying would, because it would separate the difference between each data point and the mean. So just by thinking of a hypothetical scenario, that should help you understand a little better. And I'll be honest with you, I forget this stuff all the time. So I have to do this myself too. Unless you work with this all, often, it's easy to forget this stuff. So I don't want you to memorize. I really want you to really understand it, why that would happen. But we do see the mean would be impacted by both those changes. But the standard deviation is only changed by multiplication, not by the addition part. The addition part didn't change the separation between every data point and the mean. And standard deviation is a measure of spread, right? The spread didn't change. Spread did change the multiplication bit though. Okay, so that's B. Okay, Isabel, I see you next. You're gonna help me with the next one. Let me read it first, and I'll cue you in when I need your help. So cumulative relative frequency. So this is something we kind of barely touched on, but it's not a hard concept once you get the hang of it. The figure shows the cumulative frequency graph of the number of ounces of alcohol consumed, interesting, okay, per week in a sample of 150 adults who report drinking alcohol occasionally. About what percent of these adults consume between 4 and 8 ounces? That's not too bad. 4 to 8 ounces per week. Okay, so the way this chart works, in case you guys forgot, it's cumulative, means a running total. Think of this as a running. So it's a running total. That's what this is. So for example, what this means is that 40% of people drink, I'm going to emphasize this word, at least, sorry, I lied, at most 6 ounces. So this means that between 0 and 6, between 0 and 6 ounces, that's 4% of the people. And it's a running total because, like, those who drink nothing, well, nobody drinks nothing, I guess. Those who drink 2 ounces, that's probably about 10% of the people. So that'd be 15 adults, obviously. 15 adults, because that's 10% of 150. So 15 adults of the 150 surveyed drink just 2 ounces of alcohol. 40% of the people drink 6 ounces. So the question now is, what percent of people drink between 4 and 8? So Isabel, what do you think about that one? So what percent of people would be in this group? Those who drink between 4 to 8 ounces per week. Oh, you're muted. Oh, Isabel, you're muted. I can't hear you.
Sorry. So for 4 ounces, would you get 20%?
Mm-hmm.
And then 8, I'm not sure if I'm explaining this right. And then for 8 ounces, you'd get 60.
Mm-hmm.
And so then you just do 60 minus 20, and then you get 40%, which is B.
Outstanding. That's a fantastic explanation. It's better than I would have done it. Good work.
Okay.
Yeah, 40%. So basically what you do is you got to take the difference between those two. Now the question, if I turn the question around and said, how many people drink at least 8 ounces, that would still be 40%, because then you look at how many people are above 8. Or if I ask another question like, what if someone, they really like to have a good time? So how many people like to drink at least 16 ounces? I mean, 16 ounces is like a beer or a couple glasses of wine, I guess. But how many people like to drink at least 16 ounces? Then it'll be 20%, because there's 8% who drink 16 or less. Those who drink more than 16 would be, or 16 or more would be 20%. So that's how you would have to read it. So okay, good work. Next up, Will, I'm going to have help me on the next one. All right, so let's talk about number 5. The average yearly snowfall in Chillyville, okay, that's a made-up place. It's approximately normally distributed with a mean, so it's a normal distribution. So we know the 68, 95, 99 rule all applies. The mean is 55 inches. If the snowfall in Chillyville exceeds 60 inches in 15% of the years, what is the standard deviation? Okay, so let me draw a diagram for you first to kind of help you out. So we'll draw a normal curve. We'll put 55 right here. Now this is going to be 55 plus 1 standard deviation. That's going to be 55 minus 1 standard deviation. And I know this represents 34% of my data right here. And that represents 34% of my data. Now 60 will probably be over here somewhere. And they say that if the snowfall, oh, I lied. I read that incorrectly. So sorry, Will's going to give you false information. You exceed 60 inches in 50% of the year. So that means that 60 will probably, so 15% of the year. So we know this right here is probably going to be about 16% roughly. That would make sense, right? If that's 34, that'd be 16%. And they say that that those that exceed 60 would be 16% of the data. So it seems that this right here, sorry, and they said that's 15%, but 16% is truly in there. So let me backtrack a little bit because I might be confusing you. So we know 60% data is here, but they say that 15% is 60 or more. So it means it's actually going to be a little bit over here. So 60 would be like right there. And we know that this distance right here is the standard deviation from the middle to that second dotted black line. What do you think the standard deviation would be, Will?
I said A.
I would agree with you. Very good. Interesting, the choices were so close together, right? That was done for a reason. So first, you don't want to say 5 because, again, it's that 16% that's on the right tail. If you have 34%, let me get a spotlight out. If you have 34% from here to here, that's fine. Then 60% would be over here. We're told 50% of the data exceeds 60. So that 6 is a little bit to the right of that dotted black line that represents 1 standard deviation above 55. So therefore, and the difference between 6 and 55 is 5, of course. So 1 standard deviation has to be 4.83. So good work. So I would agree with you. Okay. That's a little tricky, but that's good critical thinking problem. So I like that problem a lot. Aiden, you're gonna help me next, and I like the Northern Lights background. It's really cool. Unless you're actually really there right now. No? Okay, all right. So let me read number 6, I'll have you help me out. The figure and the density curve, the figure shows the density curve of a distribution. Some values are marked on the density curve, which of the following statements is true, okay? So obviously it's skewed. Now, Aiden, would you say this is skewed to the left or skewed to the right?
Skew to the right.
Actually, we say skewed to the left. It's a little confusing. Trust me, it took me forever to make sense of it. The reason why it's skewed to the left, well, the way we tend to look at it, it tails off to the left. But here's a real reason why we say that. This has helped me to remember, because trust me, for the longest time, even as an adult, I would constantly get this confused. Let's think about home prices in the Bay Area, right? I've used this example a lot. Home prices in the Bay Area is not really normally distributed. So it actually kind of does this. The median will probably be somewhere over here, but the mean is probably somewhere over here. So basically the mean is greater than the median. Why? Because there's probably those handful of homes in Atherton or Hillsborough, like Seth Curry bought one for $30 million, right? That's causing the mean to be pushed to the right. So you have those outliers, right? So most of that is to the left. However, when you're skewed to the left, a good example could be maybe, if I give a real easy test in one of my classes, right? And a lot of people do really well, but maybe there's like 1 or 2 people bomb it. So there's 1 or 2 people bring the mean down. So they're causing it to shift the graph to shift to the left or skew to the left. So that's how you can think of it. So this is definitely skewed to the left. Now let's look at the choices here. This is going to be a little tricky. I'm actually not 100% sure myself, so we're going to help each other out here, Aiden. Do we know where the mean is, Aiden? Is it clear?
We don't know where it is, but we can kind of, I guess, guess.
Yeah, I mean, I wouldn't say it's E though. I'd probably say it's, what would you guess probably?
F then, if it's not E.
Actually, if we push a little bit more to the left, the median would be around E or so.
Okay.
So probably more like C or D, but again, we're not really sure.
Yeah.
Because there's not enough information there to help us out. So I'm gonna cross it off.
Yeah.
The area between B and F is 0.5. Do you think we really know that?
There's no data to help with that.
Yeah, there's no data to really help, so I'm gonna cross it off. The median, I suspect the median is gonna be probably more where the peak is. Would you say the median would be at C?
No.
No. The third quartile is a 75th percentile.
Mm-hmm.
So at D, that means that if this is the third quartile, that's Q3, it means all this over here is 75% of my data. Do I know that?
No.
No. So E is the one I could say with confidence. So when you're told the area is 1, what is 1 as a percentage?
0.01 or 100.
100%. Because what's 0.5 as a percentage?
50.
50%, exactly. So I could say 100% of my data is between A and G because those are the high and lows.
Yeah.
So that's how you want to look at it. So that mind process, what you want to go through, that thought process of like going through process. Yeah. So thank you for helping me out there, Aiden. You're right. I'm going to have you help me next with number 7. Let me explain the problem first. If the heights of a population of men are approximately normally distributed, okay, so we have normal distribution. The middle 99.7% have heights between 5 and 7. What is the standard deviation of heights in the population? Now remember, we have this rule here, 68, 95, and technically it's 99.7. I've been saying 99, but we'll put 99.7. So this means this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. Let me draw a diagram for you. So here's a normal distribution. The mean's always going to be in the middle. Remember, mean and median are the same thing for a normal distribution. And you're told that the middle 99.7%, which is all the way off to the far right, is 5 feet tall and 7 feet tall. So that means that all this I'll shade in red, let's say. Let me get a highlighter out. All that right there let's go back to all this red shaded area is 99.7%. And we also know that 99.7% correlates to 3 standard deviations. So this is going to be the mean plus 3 standard deviations. 5 feet would be the mean minus 3 standard deviations. And we actually have to convert this to inches eventually, because they give the answer in inches. So let's actually change the 5 feet to 60 inches, because that's 5 times 12. And the 7 feet, I'll convert that to 84 inches, because that's 7 times 12. So the question is, what is the standard deviation of the population? So the first question I have for you, Riley, is what's the difference between 84 and 60? Just 84 minus 60.
Oh, sorry. I don't know.
No, it's okay. You're muted, but go ahead.
24.
24, right? Exactly. So 24 is the difference between these two. It's not necessarily the highest and lowest, but it's pretty close. Because there's like that 0.1. Maybe there's that one guy who's like 7'6", right? Like he's like the tallest person in the world, and someone's like super short, right? Regardless, we'll ignore midgets and giants for now. So 24. Now, how many standard deviations are these away from each other? 60 and 84.
3.
They're each 3 away from the mean. But how about from each other?
Oh, 6.
6 standard deviations. Good. So this represents 6 standard deviations. So what would the standard deviation be for this situation here?
Oh, 6 foot.
Well, if it's 24 inches between 84 and 60, and that's being represented by 6 standard deviations. So 6 times the standard deviation equals 24. If that's true, then what would each standard deviation equal?
Sorry, I don't really understand what you're asking.
So the difference between 60 and 84 is 6 standard deviations, right?
Mm.
As you just said. And so if we kind of think of visually, actually that might help. So 1, 2, 3, 4, 5, 6. How wide do you think each of these are going to be? If it goes 24 from 60 to 84 and you have 6 partitions.
Like 1 away from each other.
4 away, exactly. There'd be 4 away, exactly. So that would be how we calculate that. So you have to just use a little. We definitely have to know what's going on with. You have to know this. This is very, very important. And then after that, then it's just using a little bit of logic and even a little algebra, believe it or not. I mean, even though we haven't done much algebra in this class. But yeah, but if it helps to visualize it, if you chop it up that way, that might be a better way to understand the situation. So yeah, standard deviation would be 4 in this case. Thank you, Brian, for helping me out here. Let's keep moving. So Mel, I see you next. So you can help me out with number 8. All right, number 8. And then we're at the home stretch here, and we'll have you guys do. And by the way, the Unit 2 review is ready in school. Just so if you want to download it and print it while I'm talking about these remaining problems, feel free to do so. But it's already in Schoology under week 7. And you guys are going to be working on that in the breakout rooms in just a little bit. So Mel, you can help me with 8, but let me read number 8 first. The distribution of time it takes for different people to solve a certain crossword puzzle is strongly skewed to the right, interesting, with a mean of 30 and standard deviation of 15, okay? This is strongly skewed to the right. So it means it's gonna look kind of like that. And say the mean is 30, so maybe the mean's over here somewhere, roughly. That's 30, standard deviation is 15. So, maybe that could be like 30 plus 15 over here. Maybe we get 30 minus 15 over there. But it's not normal, mind you. So you can't say it's 34% to the right of 30, 34% to the right, left of 30. But the question is asking us the distribution of z-scores for those times So this is interesting. It's kind of conceptual. We haven't really talked much about this. This might be a little confusing. So what is the z-score? Z-score is this. And so when you calculate, and let me actually look this one more time. Give me one sec. So, for example, we wouldn't anticipate our z-scores being norm distributed because we do have that strong skew. But for the middle, if I were to calculate this z-score, what would that z-score be, Mel, if I were to compute that? So I have the calculation right here. What would I get if I calculate that z-score? Or if I just computed all this? Oh, Mel, you're muted. I can't hear you. Unless you're not there. Let's go to Gabby. It's the next person I see. Again, if I computed all this here, what would I get? But at 30 minus 30 divided by 15.
I'm sorry. 30.
Yeah. Yeah. What I have circled there?
I can't really understand it, but I think you said 35 minus 30.
No. 30 minus 30.
Oh, 30 minus
15.
30 is 0, so you get 1.
You get a z-score of 0, right?
Yeah.
Now, so that would be because the mean was 30, and z-score is defined as this. So I just do 30 minus 30 divided by that, and that's what happens. And because we're already skewed to the right, what would you think the answer for this one would be? So remember, I crossed off A and C already.
Yeah.
And they're asking what happens to the z-scores. So obviously the first z-score I calculated was 0.
0 to D.
Yeah, I'd probably agree with D. Yeah. Now z-scores are supposed to always reset. It always reset to 0 for the mean and standard deviation of 1. So that's what we kind of call like a standardized distribution, but it's still going to be skewed to the right, however. So it's D. Okay, thank you, Gabby. I'll do the remaining 2 really quickly, and I'll have you guys in your breakout rooms. Let's look at number 9. For number 9, the EPA requires that exhaust of each model of motor vehicle be tested for the levels of several pollutants. The levels of NOx in the exhaust of one light truck model is found to vary among individual trucks according to normal distribution. So always focus on that. It's normal. You have the mean, and you have the standard deviation. Which one best estimates a proportion of light trucks of a small with NOx levels greater than 2 grams per mile? Well, what I'm probably going to do is calculate the z-score. So it's going to be 2 minus 1.45 divided by 0.4. So it's 0.55 divided by 0.4. And if I use a calculator, I get 1.375. That's my standard deviation. So that's my z-score. Now remember, when you have a normal distribution, the mean's right in the middle. I'll call this mu. Remember, that was mu. That right there is mu plus sigma, which has a z-score of 1. Or z-score 1 means you're 1 standard deviation above the mean. A z-score -1 means you're 1 standard deviation below the mean. That'd be mu minus sigma. So obviously I'm more than 1 standard deviation above the mean, and I know this is 16% over here, meaning that 84% of data is less than this, but you want to be greater than 2. So I know that the answer is probably not going to be these here, because you want to be greater than 2 grams per mile. So you want something over here. So it's probably that going to be down between A and B. And my suspicion is probably going to be B. That's going to be the percentage who have greater than 2. But the best way you can do this, and there's a question in chat. No worries, take your time, John. Is we use a calculator. So if you use the TI-84 calculator, and by the way, if you want to borrow one, just ask for me an email and I'll leave one in the lockers. You can pick up anytime you like. But the best way to do this, it's going to take a little time. You can also do this in Excel or in Google Sheets as well. But remember, we go to second vars. You pick option 2. Let me clear this. And you're going to put your lower actually as 2, and you pick your upper as 1E99. So 1 second E99. So basically, you're looking at everything from 2 and forever to the right, because you want to be greater than 2. You're going to make your mean 1.45, and you make your standard deviation 0.4. You paste it, and there we go. So 8.46% of the data would be more than 2. And that's how you do it. And then if you were to do it in Google Spreadsheets, I'll go to that really quickly. Actually, let me go to Google Drive. That's going to be easier. New file. I probably have a bunch of untitled ones I'll have to delete eventually. And if you hit equals norm, remember it was acting up the other day. And I think if you type in 2, 1.45, 0.4, and I still don't know why it's not. It says what's the error? What am I doing wrong? Like I need 4 arguments. So I think we do from 2 so if I put a big number, I think yeah, something seems a little off here. I'm not sure. We do this then. Norm, this spreadsheet. There we go. if you're ever stuck, good old Google, help us out here. Okay, X means standard deviation. That's weird. Can I just do that? Okay, may I put a 0 there? Let me try it one more time. I did that last time and that didn't work. Or last class. 0.4, 0. That seems a little bit weird to me. I'm not sure what's going on. I'll need to investigate. Use a calculator. Excel, I know, does it correctly. I'm still not sure why this is acting up on me. I'm really a little bit perplexed. Yeah, because that should be correct, but I don't know why it's giving me that as an answer. It makes absolutely no sense. If that's your data point, 1.4. Yeah, because we should be getting like 0.8. Yeah, I don't know what's. Oh, okay. That's weird. Okay, I guess we have to do. Okay, I think I've tricked it. Okay, I think I've had to trick the system a little bit. I think you have to put a 1 there to make it. I think by putting a 0, I think it did this. The PDF. I want the CDF, the cumulative. Okay, so I got it now. So if you don't have a calculator, you can do it this way. You do this, but that means that 91.5% of that's to the left of 2. Want to be to the right of 2, you do 1 minus that number. That'll get you 8.5. Okay, now I got it. All right, took me a while to figure out, but just use the internet. The internet will help you out. Okay, last one, then you guys will do a little practice. 210. Until the scale was changed in 1995, ST scores are based on a scale set many years ago. Those who are curious, that's when I graduated high school. So the ST went through a change in 94. Went through another change actually in 2005 and then in 2016. So it's gone through a lot of changes. When I was taking it, and by the way, for those who are doing the SAT this Wednesday, don't worry about any homework that's due. Well, okay if you just hold off on that. I am going to make myself available on Friday if you want at 10 o'clock in the morning. I'll shoot an email for those who are in that boat, just so you know what you missed. It'll be like a short 30-minute session that'll be available. I'll shoot you guys an email by tomorrow, later today or tomorrow. And don't worry if you're missing out, about any homework due that day. Just don't do any work for my class. Focus on the SAT, focus on sleep. That's more important. It's kind of like your one chance, right? Anyway, for math scores, the mean under the old scale in the early 1990s was that. Standard deviation was 110. In 2016, the mean changed a little bit. Standard deviation was that. Gina took in 1994, scored that. Her cousin Colleen took it in 2016, got that. Who did better? That's actually interesting because the scale did actually adjust right after I graduated because they went through a change. And my score actually should be a little higher than it was. We could do that as a little trivia sometime if you guys want to figure out how I scored. As you imagine, my math was really strong. My verbal needed some work back then. But anyway, all sit straight. Happy the schools I went to, and look at me now, right? I'm teaching math. I'm married to 2 beautiful children. I'm happy about that too. So anyway, let's look here. So who did better? So what we should do is calculate the z-scores. That's what we should do. So we'll do z. Who are the people again? Gina. So z for Gina. Let's calculate her z-score. So she scored a 500 when the mean that year was 470, and the standard deviation, of course, was 110. So what was her z-score? 30 over 110. Which is going to be 0.27. Okay. Now let's calculate the z-score for Colleen. She scored a 530, so she might brag, I did better than you, I got a 530, blah, blah, blah. It's like, yeah, do whatever. Let's talk about relative, right? 530 minus, hold on, what was it in 2016? That is just really hard to read here. And 103 is the standard deviation. So it's 20 out of 103. Her z-score is 0.194. So what this means is that Gina's percentile would be higher because you had higher z-score. Remember, we can calculate percentiles. If you were to do this, if you had second bars, inverse norm, and the area, actually, No, we don't do this. I lied. That's if you want to get a data point from that. I don't know the area. What I do is I do the same thing. Second var is option 2. And we'll do 0.27. We'll leave the lower as is, and we'll keep it as 0 and 1. Remember, the mean and standard deviation are 0 and 1 respective for z-scores. So she was 60.6 percentile. So she scored about 62.6% of people who took the test that year. Whereas for Colleen, that's 0.19, her percentile was 57.5%. So you could probably say that Gina probably did better, even though she had a lower score. So I say Gina, not because the standard deviation, but because her standardized score is higher. And that's what we call z-scores, they're standardized scores. So that'd be C for that one. Okay. So that covers good review of what we've done so far. So you guys will do some review right now. So the review actually is in Schoology. Just click on week 7, and I put it right there. So I'm gonna have you guys work on this in your breakout rooms. We'll do this for about 10 minutes. We'll come back, we'll check in, and we'll be done. Don't know if you'll get to all 10 questions. And by the way, the file is pretty big. That's because there's different versions of this with the questions mixed up. So yeah, just go ahead and give it a try. Here's like 1, 2, 3, 4, 5, 6, 7. We'll see how far you guys get. So we'll do this as a breakout room of 3 groups. So stop sharing.